Swayam Prabha. Digital India. Educated India.
Today's class will take a look at continue to look at formulating nonlinear relationships, specifically how to build these table functions. We saw yesterday that can capture various nonlinear relationships using table functions. What do you mean by that? So let us see. Formulating nonlinear relations. We are going to look specifically at table function. Okay. See, what we want to do is many functions are of the form y equal to f of x, right? Some function of x, y is some particular function of x, but we do not know the exact analytical expression for this function of x. So, we specify the function as a lookup table. Because what we want to do is just say that y is got as an effect of x on y, which you are just specifying as a table just specified as a table. So, this effect we want to specify as a table. So, what we mean by a table is that we want to give these pairs of x1 comma y1, x2 comma y2 and so on, where x is your input and y is your output. We want to specify the set of values and then use it in a simulation. So, instead of specifying the function directly, we are specifying some combination, when if this is x, this is the effect of x on y, and we allow the simulation to either interpolate between these values between x1 and x2 or extrapolate if it is beyond less than x1 or greater than x2, because x1 is your independent variable, this is your dependent variable. So, this is what you are going to do. But when we specify this, given some arbitrary description, if we want to figure out how to go about doing that, so we will learn it through an example today. But there are certain steps that we can follow to come up with possible shapes for these kind of lookup functions. That should be increasing function, decreasing. There are only so many possible shapes we can give the function. So, we will kind of follow a pretty laid out procedure, which will help guide our thinking process, using which we can come up with various possible shapes for the function. So, I will just kind of read out the guideline. So, first step, let us start working with normalized input and output. In yesterday's example that we saw, if you had done a units check, you would have found an units error because we have got an input of density and output was some dimensionless fraction. So, it becomes very difficult when suppose that we want to apply it for some other scenario, then it becomes quite difficult. So, one way to overcome that is we start normalizing the input to the output. So, normalize the function so that input is the dimensional ratio of the input to the reference function. So, what we mean by that? So, steps to build a table function, or say rather guidelines, steps are guidelines. First one is we want to do is normalize. So, instead of y equal to f of x, let us use So, instead of y equal to f of x, let us use y equal to y star into function of x divided by x star. This didn't come out properly, so let me rewrite it here properly. Y equal to y star function of x divided by x star. So, in this case we are assuming your y star and your x star are known constants and they serve as our reference values. Typically we may assume that when the value is x star, then the output should be y star. Suppose we know reference value, in that case then we normalize it, saying that okay, now let us take once we normalize, this is the actual value of x divided by reference value of x, so we are normalizing it, and the output we then multiply with the reference value of y to get the actual value of y. So, this is a typical way we are going to normalize. So, the input to the function, so now the input to the function became a dimensionless ratio, and the output of the function will also be a dimensionless quantity, right. So, step 2 before we is, while we are constructing the normalization, we are going to need to have something called as reference points, right. So, for example, we may say that when x is equal to x star, it implies that y must be equal to y star. Pretty much what you are doing is you are saying that this curve passes through 1 comma 1, that is this curve which is a dimensionless ratio which is going to pass through 1 comma 1, only then we will get x, if when x is equal to x star, y equal to y star. So, these could be reference points. Does 0 comma 0 occur when x is 0, does y become 0 or y become 1? Some reference values will be known whatever the function that we are talking about, right. But remember this function, let me see, the function takes dimensionless ratio of input to input reference, and output is dimensionless effect of modifying your output reference y star. Input reference is x star, input to x star. So, the function actually takes dimensional ratio of the input x star to the ratio of the input, and output is dimensional effect of modifying your y star. So, the input and output we are kind of scaling, right. So, to get the true value on y, we need to multiply with the reference value of y star, and before we give input to the function, we are taking the ratio between the x and x star, where x star is the reference for the input. Okay. This is some example for the reference points. Once you have the reference points, suppose we have a few points, then we can think of what we call as reference policies. Suppose for example, here we say the reference point is when x is x star, then y equal to y star. This implies that the curve passes through 1 comma 1. When I think of a reference policy, then I can think of is there a meaning for say a 45-degree line, that is for a 1% change in your x value, then from the reference does y also change correspondingly same 1%? If so, then it is a 45-degree line. If it changes higher, then I am going to have a line with higher slope, or if it changes lower, then I am going to have a line with a lower slope, right. So, those kind of policies is what we are going to think about. This is just an example. It could be a 45-degree line, or 45-degree line may not make any sense. So then next we will start thinking about reference policies, and we will use these reference policies to identify possible infeasible regions. When x is very low, can y take a say value 1? If that is never going to occur, then we know, okay, these regions are actually infeasible to us. So we can use it to narrow down the possible shapes for the function, or possible values the function can take. So along the reference policy, we also need to think of what happens at the extremes. When x takes a really low value, say like -infinity, then is there a value that y should take, or is it when x goes less than 0, what happens, at 0 what happens, at +infinity what happens, so that whatever values that x is going to change, because we don't know in actual simulation what is going to happen, we don't know, but the output of y should make some sense, right. So then we think of these extreme conditions. So though we are starting here, there is a hidden step which I didn't mention in normalize. While we normalize, first we have to identify our y star and x star and start identifying what are those ratios first, right. So that will be like hidden step 0, then we normalize. We will learn it through an example. So let us go back to our slides. Step 1 is to normalize, step 2 is identify reference points where values of function determined by definition. Identify some reference policies, these are lines or curves corresponding to standard or extreme policies that you are aware of. You can use this to identify infeasible regions. Then we consider extreme conditions. Yeah. From reality, from theory, from stated reasonable expectations, yeah. Correct, yeah. If it is based on some assumption, that assumption has to be based on something, right. Why are you assuming that? Is it something reasonable to assume? Is it supported with some theory or something? Then we go with it. The next guideline, specify domain of the independent variable. We told x is the independent variable, so what is its domain? It is going to take value between 0 to 1, -infinity to +infinity, or 0 to infinity. What is the range? So that we can operate within that. What happens if it goes outside? It's clearer. Once we do that, then we start to identify possible shapes of the function within the feasible region. Then we specify values for our best estimate of the function. Use increments small enough to draw the shapes, get the desired smoothness. Then based on that, run your model and test behaviors for the various formulations. If you have a couple of different curves, we can try to simulate and see whether that behavior changes drastically based on that actual curve values. Many times you are interested in the actual behavior of system, may not be particularly interested in the last final value. So to see the patterns of behavior, it may not be that sensitive to the shape of the curve. Check if input moves outside the range, etc., so that we can identify errors. Then test sensitive results to possible variations in the shapes as well as the values of the function. These are general guidelines to build a table function. It's too much to remember everything right away. So let us learn it through an example, or let us take up some simple scenario and try to go ahead on how we can think it through and build some possible shapes. Let us consider an example. Let us consider a firm operating make to order system. Orders accumulate in backlog until they are completed and shipped. So as soon as order comes, they go into backlog, and then product production is determined by the backlog and target delivery delay. So as soon as order comes, is put in backlog, then people to take a look at the backlog and they say, okay, based on target delivery delay and the backlog, they are going to determine the production rate. Shipments are determined by the size of the production rate by limited by firm's production capacity. Okay, it's quite obvious to see that there is only one stock, backlog. So as soon as order comes, it goes into backlog, right? As long as you see the backlog exists, then people start to work, and based on the target delivery delay, they decide to work faster or slower. And once they complete the work, they have to ship it. The shipment is determined by size of production rate, but limited by the firm's production capacity. So, desired production rate can be defined as backlog divided by target delivery delay. Now, but shipment is a function of production, desired production, function of capacity, that part is not clear. So, one other thing you might have all encountered is, you must all have visited McDonald's, KFC, Pizza Hut, right? They are all make to order, right? They don't make things beforehand. That's exactly what is happening. The firm, order comes, as soon as its order is there, then they start producing. I'm sure they have some benchmarks. When you order this, it should take so much time. So based on that, they start to work. But their pace is limited by their capacity, right? And then they are going to, and as soon as order is delivered, then you take it and leave, right? That is pretty much the system that we are trying to model here. But now, what is the shipment rate that is going to be governed by the production speed or by their based on desired production? Desired production is based on customer orders, right? During rush hour, there is a lot of orders, but also it's also defined by their capacity. If there is only some 3 people working, you know how long it is going to take. Whether if there is only one person is going to work, then that's the time it is going to take, correct? So it is, so that is a kind of real life analogy you can think of. And if you have been looking at system there, even the order is very visible. They usually type it in the computer and it gets visible in the room, in the back end, or they put kind of post-it kind of things also, they put tags, they put, and that's when they actually see. That's literally the backlog that you are seeing there. And for each activity, they usually have benchmarks saying what is going to be target delay. You know, once order comes, it's a fast food joint, so they have to ensure it is fast. So maybe instead of, in this example, it says a week as a time unit, but it could be a 5 minutes or 1 hour or whatever it is. Pizza is 40 minutes, so supposed to reach you in 40 minutes, right? So it's defined by the capacity as well as the desired production. So that's what we are going to do, and we are going to follow the same steps that we saw in defining this. First, let us draw this example. So let us get a stock flow visualization of the model. So let us go with a very familiar with this, so let's stick to that. Orders come in, shipments, reduce a backlog. Based on the backlog, we have already told that we have something called as desired production. Desired production is also influenced by target delivery delay. Then we have the normal capacity. There is a reason why I am calling it normal capacity. This is the kind of model we have right now. Let us call this desired production, target delivery delay D star, delivery delay D star, normal capacity as I think you can just keep it as C. If you want to measure the actual delivery delay, then how will we do it? How will I compute it? Target delivery delay is an input given. What is the target, the delivery delay? How will I measure it? Huh? What is it? Yeah, so in this, how will I compute it analytically or simulate it? Yeah, backlog divided by shipment should give you a delivery delay, right? So, we can just keep it as delivery delay DD backlog divided by shipments. Here desired production divided by target delivery delay. So, let us put a minus there. This is a setting that we have. What are backlog? You can just call it B for backlogs. So, in this, say suppose the backlog you are measuring in terms of say bottles or something. So, if that is a unit of measure, then desired production is bottles per week is what they are producing. So, then what should be unit for capacity? How do you measure capacity? Huh? The same units as production. Capacity also can be bottles per week, assuming bottles or widgets or SKUs or burgers or pizzas, whatever, boxes or cartons, whatever the unit you are taking for backlog, the same units is backlog by say cartons per time. Capacity also will be say cartons per time, the same units gets followed. Now, we want to do the first step of normalizing it, right. So, some of these equations are known, what we do not know is if you know for a fixed capacity and fixed production values, then we can compare it, but that is going to keep changing, that is the production is going to keep changing, right. Now, what do we want to normalize? This is what we want to normalize. So, we have shipments is a function of desired production, shipments is a function of capacity. This is what we want to normalize. Okay. Let us see how we go about trying to do this normalization. Let us go in the reverse. So, let us define a new variable called as say capacity utilization. Okay. Let us define a variable called as capacity utilization. Many of you will come across capacity utilization. So, what you are saying is how much of the capacity has actually been utilized. So, once you define that capacity utilization, then your shipment should nothing but a product of the normal capacity multiplied by the utilization of the capacity, correct. So, how much of the capacity I am using? I am using 80% of the capacity. That means the shipment should be 80% of the capacity into the actual capacity, right. So, that should give me your shipments. So, based on that, let us define shipments as normal capacity multiplied by capacity utilization. Yeah. So, this normal capacity we already know, capacity utilization is what we do not know, but you already got something which is a dimensionless effect of the outcome, which is reference value y star. So, this is your outcome of your function f of whatever it is, right. So, this is outcome of the function, which is dimensional effect of the outcome on the reference value, right. So, this is a dimensionless output. Now, let us see the input side. On the side of the input, we have desired production. Okay. At any point, we will be able to compare the desired production versus the capacity on hand, correct. Suppose I have orders for 1000 and I have capacity to do 1000, then I am saying, yeah, I am good. Or if I have capacity to do 1000 and my desired production is only 500, then I know I am over capacitated, right. I have enough bandwidth to complete that order, correct. So, that means what we are doing, we are actually comparing the desired production with the normal capacity. Okay. and if, since both are the same units, suppose you take a ratio of it, then we know as compared to the normal capacity what is my desired production, is it above that or below that, or how far much below or how far much above, I can make the comparison, correct, and then relate that with my capacity utilization. So, now let us define ratio of desired production divided by normal capacity. So, this ratio you can come up with some name. So, why both are different? Suppose desired production is lower than my normal capacity, then we say okay, they must be able to produce the order in the as per the target delivery delay. If the desired production is much larger than the capacity, then we don't know they will produce as per capacity, but it never typically works like that, and it is because as we get busy and busy, things what can I say, your marginal improvement comes down, right. So, this is the total activity that you need to do within the given time based on this capacity. So, let us just call this ratio by a new term called as schedule pressure. Now, finally, the normalized function or the table function is going to be defined, table function will be defined for this term where capacity utilization is a function of schedule pressure, which is nothing but a function of desired production by capacity. And we look at it when we want the final shipment, it is nothing but normal capacity into capacity utilization, which is capacity into function of desired production by its capacity, is what we are going to build. So, the table function we are going to build is what should be the capacity utilization as schedule pressure changes over the normal capacity. When schedule pressure is very low to the capacity, then what should be value of utilization? If schedule pressure is comparable to capacity, then what is the utilization? If schedule pressure is higher than capacity, then what should be the utilization, right. So, those are things that we are going to think about. So, now both input and output are now became dimensionless. Now, let us modify our SD model to represent this. Desired production, target delivery delay, and we are defining a new variable called as schedule pressure. This is function of that as well as the capacity. Then we have a capacity utilization. So, lack of space, I am just writing it like this, plus minus plus 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 So you see, let's call it SP, yeah, then we already have our delivery delay also. Okay. So this is how our model is going to look. The only changes are here, schedule pressure and CU has been added and causal links are made so that we can get all the functions that we just wrote in the previous slide. The step 2 is to identify the reference points, right. So that is our step 2. Now there are a couple of ways to define these reference points and policies.